Alright, welcome to lesson 15 of MA 103, where we do parametric equations 1, and I introduce you to the vector equation of a line. And so right now, I think if I asked most of you for the equation of a line, you would give me something to the effect of y is equal to mx plus b, right, the old slope-intercept form. And so today we're going to introduce you to this vector equation of a line, which looks a little bit different, but not too much. So r of t is equal to r naught plus t times v. And so first what I want to do is I want to highlight the similarities. And so if we think about this b parameter, that's just the y-intercept. It's a point on the line, right? It just happens to be when x is equal to 0. Similarly, this r naught vector, that's a position vector to a point on the line. That's all it is a starting place. It's a point that we know is on the line, right? And then next we'll look at slope. And so slope, we know something about the line just by looking at the slope, right? If it's a small number, then we'd expect to see a relatively flat line. If it's a really large positive number, then we'd see a very steep, rapidly increasing line. Or if it's a negative value, then we'd see some kind of decreasing line. And so that relates to this direction vector. The direction vector tells us the orientation that our line is headed, right? And then the last things that we have here are our independent variables, right? So if we want to find a value or a point on the line, we can substitute a value in for x and we can find the y. Similarly, with this vector equation of a line, if we want to find a point on the line, we can pick any value for t, substitute it into the equation, and we can find a position vector to that point on the line. Okay, and so I'm going to carry this example a little bit further. I'm going to give you a equation of a line 3x plus 2. And we're going to find some points, right? And so the easiest points would be when x is equal to 0 and maybe when x is equal to 1. And so if x is equal to 0, then y is equal to its y-intercept 2. And if x is equal to 1, then y is equal to 5. So we've got these 2 points now. We've got 0, 2, and we've got 1, 5, right? And so now I want to figure out, how do I make the vector equation of a line out of these 2 points? Okay, and so I'm going to draw this graphically for 1 second. And so now I've got these 2 points plotted, and I'm just going to go ahead and label this first point A and this second point over here B. And so I told you guys that r naught is just a position vector to a point on the line. So we can pick either point and express it as a position vector, maybe something that looks like this, to the point A. So I'm going to go ahead and substitute 0, 2 into our equation, right? Plus t times, I told you v was a displacement vector, and all it is the displacement vector for us to get from A to B, right? So we want to find this displacement vector right here. And so if we're trying to find, if we want to find AB, all we have to do is B minus A, right? So I can write out 1, 5 minus 0, 2. We can find this displacement vector, which is equal to 1 and 3, right? So that's my displacement vector. And so now I'm going to substitute that in here, 1, 3. And now using this equation right here, I can get to any point on the line, right? So, if t is equal to 0, then where am I? Well, I'm at point A. If t is equal to 1, then now I'm at point B. If t was equal to 1/2, I'd be somewhere out here. If t was equal to negative 1/2, I would be on the same line, just now I'm in the opposite direction. Or t could be negative 1, and now I'm somewhere down here, right? And so I can get to any point on the line using this vector equation right here. So now let's consider the question of, so we have this equation of a line, but I want to find the equation of a line that's parallel to this one, but goes through a specific point. So I'm going to rewrite our equation over here. So we've got r of t is equal to our position vector 0, 2. And this is a little sloppy. so is equal to our position vector 0, 2 plus t times our direction vector, which was 1, 3. And so I want the equation of a line that goes through this point, let's say point A, which is equal to 12 minus 5, right? So I want it to be parallel, but go through this point. So what does it mean to be a parallel line? Well, if we look back over here at this example of slope-intercept form, we would just say, oh, well, it has the same slope, right? And that's just pretty similar to what we're going to deal with in vector equations. We need it to have the same direction vector. But, is vector 1, 3, would another vector 2, 6 be parallel to vector 1, 3? Yeah, absolutely. So any scalar multiple of this vector is still parallel to it, right? And so it's got to go through this point. Well, what's one way that we could ensure it goes through that point? Well, we could set that point as R naught, right? And so could we just do this? We could say, I'm going to call this S of t, so it's a different line. So we'll say S of t could be equal to 12 minus 5 plus t times 1, 3. Does that satisfy a parallel line that goes through the point 12 minus 5? Well, if t is 0, we're at this point, right? So if t is 0, we're at that point. If t is any other value, we're on the line, but we know that because they have the same direction vectors, we're parallel. All right, so now what I'm going to do is I'm going to transition to a new problem, and we're going to look at finding the angle between two intersecting lines. And so if I scroll down here, we can reset. We've got a new problem, and we see this R1 of t and R2 of t, and clearly they intersect, but we want to figure out the angle at which they collide. Okay, and so the first thing we need is the equations for these two lines. And so I can look at the plot, and I can see a couple of points that are easily identifiable. Maybe it's this point out here, which would be 0, 5. And maybe it's this point where they intersect down here, and we'll call that point 4, 3. Right? And so there's 2 points, so I can figure out the equation of R1 of t. But I need to identify one other point real quick on R2. And so maybe as I look, I can identify this point over here, and we'll call that point 1, 2. Now I've got 2 points for each of the lines, and I can go ahead and figure out the equation of these lines. So do the first one here. We'll do R1 of t. So we can say, switch back to black here. Say that R1 of t is equal to, well, R naught, right? So this first term is R naught. And then we know it's going to be plus t times this direction vector v. So R naught, I can pick any point. So I'm going to pick 0, 5. Plus t times a direction vector. And so how did I get from 0, 5 to the point 4, 3? And if we need to, we can just figure that out by doing 4, 3 minus 0, 5. When I do that, I'm going to get 4 minus 0 is 4, 3 minus 5 is negative 2. And so that is my direction vector. Now I'm going to do the exact same thing for R2 of t. And so I'll let R naught be that point 1, 2. Plus t times my direction vector. And again, I've got to get from the point 1, 2 to the point 4, 3. So that means I'm going to do 4, 3 minus 1, 2. That gives me a value of, let's see here, we got 4 minus 1 is 3, 3 minus 2 is 1. And there's my direction vector, 3, 1. All right, so if we have my equation of both lines now, I've got to figure out how am I going to determine this angle of intersection. And I look at these two equations, right? So there's R1 and R2. Do I need this R naught value to tell me anything about the angle of collision? The answer is no. I don't. All I care about is I know that they're going to intersect, And so what is the direction that each line is headed after they intersect, right? That's all the information I need. So all I'm going to be working with in this problem is these direction vectors. And so if you said to yourself, I bet we're going to go back to the way we solved for the angle before, where we said that the dot product of A and B was equal to the magnitude of A times the magnitude of B times cosine theta, then you'd be correct, right? And so what I'm going to do is, for in the interest of this problem, call this vector A our first direction vector, which was 4 and -2. And B is our second direction vector, which was 3 and 1. And so if we want to go ahead and compute the dot product of this, we can do that, right? And so we can say A dot B is going to be equal to 4 times 3 plus -2 times 1. So that gives me 12 plus -2, which equals 10, right? The other thing we need is we need the magnitude of A. So I'll do that right here. Magnitude of A is going to be equal to the square root of 4 squared plus -2 squared. So that's the square root of 16 plus 4, square root of 20. And we'll go ahead and find the magnitude of B, which is going to be equal to the square root of 3 squared plus 1 squared. So it's the square root of 9 plus 1, square root of 10. Okay, so now I'm going to substitute these values into our equation. And so we already know how to manipulate this equation right here to solve for cosine theta. Right? So if we want to find theta, all we're going to do is we're going to say theta is equal to arc cosine of the dot product of A times B over the magnitude of A times the magnitude of B. Right, so we can substitute our values in. We'll have 10 divided by the square root of 20 times the square root of 10. And when you solve this in your calculator, making sure that your setting is in degrees and not radians, you should get an answer of 45 degrees. And so that is the angle of collision for these two lines. Alright, so now what we're going to do is we're going to move over to a new problem once again. And so what I'm going to do is I'm going to give you this equation of a line. So S of t is equal to the vector 2, 4 plus t times -3, 1. And I want to know if the point P, which is equal to -16, 10, is on the line. And so what I've done is I've kind of sketched out what this line may look like using 2 points. And a lot of times our students want to determine if the point's going to be on the line by sketching it. And that's easy if we only give you 2 dimensions, but if it's a 3-dimensional problem, if we include the z component, then drawing becomes very challenging. And so we've got to be able to solve this algebraically. And to do that, what we know is that if the point is on the line, then there's some value of t that would generate the point, right? And so, or a position vector to that point. And so what we can do is we can set the point P equal to the right-hand side of our equation. And in doing that, we would do something like this. It would say -16, 10 should be equal to this vector 2, 4 plus t times -3 and 1. Alright, so what we can do to try to simplify this is we can subtract this vector 2, 4 from both sides. Oops. And so when we do that, now what we've got is, so -16 minus 2 is going to be -18. And then 10 minus 4 is 6. We say that equals t times -3 and 1. Right? And so this first entry, this -18 and this -3, that corresponds with the x component of our line. And then the second term corresponds to the y component. So I'm going to break this into a system of 2 equations so that we can solve for t. And so what that looks like is -18 would be equal to negative 3t, and 6 is equal to t. And so I don't have to go any further in solving because I already know that t is equal to 6 from this bottom equation. But what I need to do is I need to substitute that value into this top equation just to make sure that I get a true statement, right? So if I substitute that in, I'd have something that looks like negative 3 times 6, which is equal to negative 18. And so since that is a true statement, we know that this point is on the line. So let's try this problem one more time, but now I'm going to give you a different point. And so we're going to use this point P is equal to 19 and 5. All right, so we're going to do the same thing. If we want to test to see if it's on the line, then we would set it equal to the equation. 19, 5 is equal to this vector 2, 4 plus t times negative 3 and 1. Right, so we're going to do the exact same thing. We're going to subtract this vector 2, 4 from both sides. So that's 19 minus 2, so we get 17. And 5 minus 4 is 1. Is equal to t times negative 3, 1. Right, and so now when I break this into a system of equations, I get 17 is equal to negative 3t, and 1 is equal to t. And so, again, I've solved for a value of t. Now I've got to verify that I get a true statement when I substitute it in here. And doing that, I'd get negative 3 times 1, which is negative 3. And so this is not a true statement, right? And so 17 does not equal negative 3. So my conclusion here is that this point is not on the line. And so maybe what we want to do is we want to find the closest point that is on the line to this point P. Okay, and so how are we going to do that? Well, on your formula reference card, we give you a formula to do it, but I want to show you how we've derived that first. So here's the equation that we give you on the formula reference card, and it says the closest point on the line to the point P can be found by taking r naught plus t times v minus p, dotting it with the direction vector v, and setting it equal to 0. And so if we think about this first expression in here in parentheses, that's a vector plus a scalar times a vector minus a vector. It's just a vector, right? And so a vector dotted with another vector set equal to 0. Well, why do we set it equal to 0? Well, if the dot product of two vectors is equal to 0, then we know that these two vectors are orthogonal. And so now I'm going to look at this graph that I drew of the line initially, and we're going to talk about deriving this formula real quick. Okay, and so imagine there's this point P up here. Right? So that's the point P, and I want to find the shortest or the closest point that's on the line to this point P. And so you may think, oh, well, we could just drop straight down vertically, and that's the point. Maybe I want to go out horizontally, and that already looks like a bad idea. But the closest path, or the shortest distance to the line, is going to be if we go orthogonal to the line, right? And so we want to find this distance, and so we'll call this point, the closest point, Q. Right? And so we know that Q is on the line, and so if Q is on the line, then there's some R naught plus T times V that gives us that point. Right? And so now what we want to do is we want to figure out what is this displacement vector that gets me from P to Q. Right? So how do I find this vector right here? And if I want to find a displacement vector PQ, then I know I can just solve Q minus P would give me that displacement vector. Well, Q was found by doing this, R naught plus T times V. So now what I'm going to do is I'm just going to combine these things. This displacement vector PQ is really just equal to R naught plus T times V minus P, right? And so that's my displacement vector. And now if I take this expression, this displacement vector, and I dot it with the direction vector v of my line, set it equal to 0, now I can ensure that I've picked a point on the line that makes this or the direction vector or the displacement vector from P to Q orthogonal to the line. Okay, and so a lot of words. Now we'll walk through an example. Okay, and so I'm going to rewrite everything that we have for this given problem here. So on my point, P is equal to 19.5. R naught was equal to 2.4. My direction vector V was equal to -3 and 1. And that's all I need for this problem, right? So now we'll substitute it in. It's going to look like this. So we've got 2.4 plus T times -3, 1, minus P, which was 19 and 5, dotted with the direction vector, which was -3 and 1, set equal to 0. Alright? And so now what I'm going to do in order to solve this is I'm going to distribute this dot product to each term inside the parentheses. So I'm going to do the dot product of this, dot product of that, and the dot product here. And then I'll collapse and simplify all of these terms. So here we go in distributing that dot product. We're going to do, the first thing would be 2 times -3 plus 4 times 1. And then that's going to be plus, let's see, 9t plus 1t minus, and I'm going to put this whole expression in parentheses here, so 19 times -3 would be -57, and then 5 times 1 is 5, so plus 5, set equal to 0. And so let's go back and simplify some of these terms. So we've got -6 and 4 should be -2 plus 10t minus -52 equals 0. And so we can simplify this to 10t plus 50 is equal to 0, or 10t equals -50. So t is equal to -5. Right, so now I've found t, but I haven't found the closest point q. I can't find that until I substitute it back into the equation of my line. And so now what I do is I rewrite, and I want to find s of 5. So we can say s of 5 is equal to R naught, which was 2.4, plus -5 times my direction vector, -3, 1. Right, and so we can do some scalar multiplication here, and so that's 2.4 minus this vector, which will be 15, and minus 5. And actually, because I carried this negative, it should say plus 15 and then minus 5. And so we simplify down, we get this point 17 and -1. And so this right here is the closest point on the line to the point P, which was not. And if we want to figure out how far away it is, now we can just use the distance formula, because we've got 2 points, and so we can find the distance between the point P and point Q. So just to label this again, this is Q.